In the year 1654, in the town of Magdeburg, Germany, a crowd gathered to witness an extraordinary experiment. The air buzzed with anticipation as Otto von Guericke, a scientist, engineer, and mayor of Magdeburg, prepared a demonstration that would challenge the very understanding of invisible forces. Before him stood two large copper hemispheres, polished and fitted perfectly together to form a hollow sphere. To the untrained eye, they were merely metal shells pressed together, nothing more. But von Guericke was about to reveal the unseen force that held them in place. With a contraption of his own invention, an early air pump, he began to extract the air from within the sphere. The crowd saw no change at first, only the slow, deliberate pumping as the device worked to remove the air inside. Then came the test. Two teams of horses, 8 on each side, were hitched to the hemispheres and given the signal to pull with all their might. The horses strained, their hooves scraping against the cobblestones, their muscles quivering with exertion. The crowd held its breath as ropes creaked and dust kicked into the air, but the hemispheres would not budge. It was as though some invisible hand held them fast. Only when von Guericke allowed air to rush back inside did the hemispheres separate with ease, falling apart in his hands as if nothing had ever held them together. Gasps and murmurs rippled through the crowd. There was no glue, no clasp, nothing but the weight of the atmosphere itself pressing in on the evacuated space. What they had witnessed was a revelation, the power of air, an ever-present but often unconsidered force, capable of exerting immense pressure on the world around us. Beneath the spectacle of straining horses and immovable metal lay a simple but profound scientific principle, the interplay of three essential elements. Each played a vital role in the experiment, and together they formed a system that made the demonstration possible. The first element was internal pressure, the air inside the sphere, which could be altered using von Guericke's pump. Before the air was removed, the internal pressure matched the external atmospheric pressure, and the hemispheres could be separated easily. But as the pump extracted the air, the pressure inside dropped significantly, creating a vacuum. The second element was external pressure, the ever-present force of the atmosphere surrounding us. Though invisible, this ocean of air exerts a substantial force on everything at the Earth's surface. Under normal conditions, we do not notice this pressure because it is equal on all sides of an object. However, when von Guericke removed the internal air, he disrupted this balance. The external air now had nothing inside the sphere to push back against it, and so it pressed in with overwhelming force, holding the hemispheres together as though welded. The third element was the airtight boundary created by the smooth edges of the hemispheres. This boundary was critical. Without it, air would have seeped back into the sphere, neutralizing the vacuum and allowing the hemispheres to fall apart. The boundary ensured that once the air was removed, it could not return unless deliberately allowed in, maintaining the pressure differential. Each of these three elements, internal pressure, external pressure, and the airtight boundary, was essential. Without the vacuum inside, there would have been no pressure difference to drive the effect. Without the weight of the atmosphere surrounding the sphere, there would have been no force to hold the hemispheres together. And without the sealed boundary, the system could not have been maintained. Von Guericke's experiment was more than a spectacle. It was a profound demonstration of fundamental physical principles that extend far beyond the Magdeburg Hemispheres. The three elements, internal pressure, external pressure, and boundaries, interact across countless physical systems, forming the foundation of atmospheric science, engineering, and even biological processes. Take, for example, weather systems. When a region of air heats up, its internal pressure decreases, much like the vacuum inside the hemispheres. The surrounding atmosphere, still at a higher pressure, pushes air into the low-pressure region, generating winds. But what defines and sustains these pressure differences? The boundaries between air masses, fronts, storm walls, and even geographic features like mountains shape the movement of air and determine whether these pressure differences persist or dissipate. Just as the airtight boundary of the hemispheres allowed the vacuum to remain stable, meteorological boundaries can sustain pressure differences long enough to fuel massive storms, hurricanes, or jet streams. In human respiration, we also find this triadic interplay at work. When we inhale, our diaphragm expands our chest cavity, increasing its volume and lowering the internal pressure in our lungs. Air rushes in due to the higher external atmospheric pressure. However, this process would be impossible without a crucial boundary: the pleural membrane surrounding the lungs. This flexible yet sealed barrier allows pressure changes to occur within the lungs, while preventing air from leaking into the chest cavity. If this boundary is compromised, such as in a punctured lung, the pressure differential collapses and breathing becomes impossible. Here, as with the Magdeburg Hemispheres, the airtight boundary is not merely incidental, it is essential to maintaining the system's function. Engineering systems similarly depend on all three elements. A steam engine, for instance, operates by creating regions of high and low pressure, using steam to drive mechanical motion. External atmospheric pressure plays a role, but the system would fail without strong, controlled boundaries, like boiler walls and piston chambers. If these boundaries rupture, the carefully maintained pressure differential vanishes, and the system loses its ability to do work. This principle extends to vacuum-sealed packaging, where external air pressure keeps food fresh only as long as the seal remains unbroken, and to submarine hulls, which maintain an internal pressure to counteract the immense external pressure of deep-sea environments. Even something as simple as drinking through a straw depends on the same forces. When you create a low-pressure area in your mouth, atmospheric pressure outside the straw pushes the liquid upward. Even in space, where external atmospheric pressure is absent, this triadic relationship still holds. A spacecraft's internal pressure must be carefully regulated, but the vacuum of space is meaningless without a boundary defining where that pressure begins and ends. The airtight hull of a spaceship is not just a container, it is an active participant in maintaining the balance of forces. If it fails, the pressure inside suddenly has no external counterforce, leading to catastrophic decompression. Just as von Guericke's hemispheres relied on their boundary to hold the vacuum and external pressure in opposition, a space station's hull is what allows astronauts to survive the abyss of space. In all these examples, pressure differences drive motion, force, and function, but they only persist as long as an airtight boundary controls and defines the system. The Magdeburg Hemispheres were not simply about pressure, they were about the power of containment. Whether in storms, lungs, engines, or spacecraft, the interplay of pressure and boundary is what makes controlled environments possible. Returning to von Guericke's demonstration, we can now fully appreciate the forces at play. The spectacle of horses straining against an invisible force was not merely a display of strength, it was a testament to the unseen power of the atmosphere. By creating a vacuum, von Guericke allowed the external air pressure to act unopposed, revealing its true magnitude. The demonstration did not invent a new force, it merely exposed one that had been present all along, unnoticed and taken for granted. This experiment serves as a broader lesson in science. The most powerful forces are often the ones we do not immediately perceive. Whether it is atmospheric pressure, gravity, or the fundamental interactions of particles at the atomic scale, nature is filled with invisible influences that shape the world in ways we rarely consider. It is also a lesson in the power of methodical experimentation. Von Guericke did not simply assert that air had weight or that atmospheric pressure was strong. He designed an experiment that forced the truth to reveal itself. This is the essence of science, creating conditions that allow the underlying principles of reality to become undeniably evident. Finally, the Magdeburg Hemispheres remind us that understanding natural forces allows us to harness them. From vacuum-sealed packaging to high-speed aerodynamics, from the physics of deep-sea exploration to the design of life-supporting environments in space, our ability to manipulate pressure and containment defines much of modern technology. Von Guericke's experiment was not just a moment in history, it was a glimpse into a world of possibilities, unlocked by the simple act of removing air from a hollow sphere. His demonstration did not just prove the strength of the atmosphere, it proved the strength of human curiosity, ingenuity, and the relentless pursuit of knowledge.